Hi, my name is Sumi Vora, and today I will be presenting on affine group schemes for my Math 176 final presentation. And so the way that this presentation is going to go, I'll give some motivation and background, and then construct affine group schemes with a few examples. And then I'll present on an important lemma that shows that affine group schemes are actually meaningful, and I'll show how you can actually define affine group schemes, which is this like geometric thing, purely in terms of an algebraic thing called Hopf algebras. And then finally, I will give like a short kind of hand-wavy example of why we would want to use Hopf algebras to talk about affine group schemes. And so let's get started. The way that we will motivate affine group schemes is to start by thinking about affine varieties. And so from class, we have a polynomial ring R with entries from some field F. And then we have some prime ideal I that contains certain polynomials that we want the solution for. Then an affine variety is the set of points in affine space that are solutions for those polynomials, right? And we noted that if you look at the quotient R mod I, then every polynomial in that quotient can be thought of as a polynomial whose pre-image is just the points in the affine variety Zi. And then in class, we talked about Zi in terms of like its topological properties, right? But for affine group schemes, our motivating question is going to be more of like whether we can describe the algebraic properties of Zi. And so just as a little motivating example, we're going to consider a polynomial ring on four variables, x11, x12, x21, x22. And then our prime ideal is going to just have one polynomial, x11, x22 minus x12, x21 minus 1. So the things in Zi in this case are basically just the 2 by 2 matrices with determinant 1, right? Because I can just sort of like arrange the indeterminants as a matrix, and like we discussed earlier, Ro is going to have all the polynomials whose pre-image is in the set of 2 by 2 matrices with determinant 1, basically. Um, Okay, so now we're going to consider a ring homomorphism from O to F, and we're going to call it phi. And then we can think about where phi sends the generators in O. So let's say phi maps a polynomial x11, or like f of x equals x11 or whatever, to A, and then it sends the polynomial x12 to B, x21 to C, and x22 to D. And then, because it's like a homomorphism that preserves the relations of the ring, then we must have that AD minus BC equals 1. So if we arrange these in a matrix again, we'll see that phi sends something in Zi to another point in Zi. And in this case, Zi is just the group SL2F, the standard linear group of simple linear group, I think simple, of simple linear group of dimension 2 with entries from F. And also, if you think about it from the other way, right, if you pick something in the simple linear group with entries from F, SL2F, i.e. Zi, and then notice that we have this unique homomorphism, phi, that comes from this matrix, because we know where phi takes all of its generators. It takes x11 to A, x12 to B, and so on, right? So we observe that there's a one-to-one correspondence between the set of homomorphisms between O to F and the group SL2F. And what we did in order to get SL2F again is we took like all of the points in like A4F, right? The affine space of dimension F that satisfy x11, x22 minus x12, x21 equals 1. And so our questions now are A, how do we do this in general? Can we do this in general? And B, what kinds of groups can be described in this way? So I guess like given a random group, can you describe it as like the homomorphisms from some coordinate ring to F? And so the goal in this presentation is to give you a good answer of the first question, how do we do this? And then maybe it will start to answer the second question a little bit. Okay, so now I'll just define affine group schemes. But first, I'm going to have to construct something called functors. And so functors, we're going to let R be a polynomial ring, or maybe it's like useful to think about it as a vector space with some sort of like bilinear product operation. And so we're going to have entries in R from a commutative ring K. And then we're going to let G be a map that sends R to group GR, such that it preserves the identity map and it also preserves ring homomorphisms and compositions of ring homomorphisms. So, i.e., if you have a homomorphism between two rings, R and S, then this is going to just induce a group homomorphism between GR and GS. And also, if you compose these operations, it's just going to like play nicely with G, as you can see here. Um, and if those things are true, we can call G a functor from rings to groups. Okay, so a couple of examples. The first one, it doesn't really do anything, but we'll say that G sub A sends R to the additive group R plus. So this one just takes R and says, okay, we're now going to just treat it as like an additive group rather than a ring. And then the second one is also kind of a simple example. It takes R and sends it to a multiplicative group, G sub MR, where G sub MR is just the group of invertible elements in R. I think like R cross is like the common notation for that. And so, okay, just as a quick note here, I'm calling R a polynomial ring, but in reality, it is like supposed to be a K algebra where K is a commutative ring. And so I'm losing like a little bit of generality. And so most of the examples, I'll just let our R be like some field. But in reality, you could have like vectors and such. So like in general, like it's sufficient for it to be a ring. So I'll call it a ring. But if it feels better, you can just like abstract away the R and just think about it as your like constants K. Okay. So now to tie it back to affine varieties, we're like interested in functors G where GR is a group of solutions to a family of polynomial equations. And so for example, we talked about G sub MR. Well, that's just a group of x's that are a solution to xy minus 1 equals 0 because we like only want to include the invertible elements of R. So what we can do is we can take the coordinate ring kxy mod xy minus 1, or like the ideal generated by xy minus 1, obviously. And then we can let phi be a homomorphism from O to R. And then the polynomial f of x equals x is an O. So for every R in G sub M R, you can find a homomorphism from O to R that maps x to R. Right? Because like if x is invertible, then you can find then there's a homomorphism that's going to map x to R because it's in the preimage. But if R is like 0, for example, then no such homomorphism is going to exist because it wouldn't like preserve the relations in O. Also, if you think about it on the other hand, um, because x is like the only generator in O, like because x depends on y, or like y depends on x, I guess, there's like a unique phi that maps x to R. Because like once you tell us where like phi goes, you kind of like have already decided where phi sends all the rest of the elements. Or like if you tell me where x goes, I've decided where phi sends all the rest of the elements because x is like the only generator. So again, like the point is that we see that the homomorphisms from O to R is like isomorphic to G sub M R in this case. Right? And so now finally we get to define like the definition of affine group schemes. And the idea is that an affine group scheme is a functor G from polynomial rings to groups, such that there is a coordinate ring O, where the set of homomorphisms from O to R is isomorphic to GR. So essentially, an affine group scheme is going to be functor G that sends R to a group of some like polynomial equations over field K, or over a commutative ring K. And if we have this, we'll say that O represents G. So again, yet another example. If we take O to be this quotient ring, K x11, x12, x21, x22y, and then mod it by the ideal generated by x11, x22 minus x12, x21 times y minus 1, then this is going to represent the functor GL sub 2, which is just like the general linear group of 2 by 2 matrices with non-zero determinant. Um, and we can see that any homomorphism from O to R, where R is like wherever the entries are coming from, will send the generators x11, x12, x21, x22 to like some element in GL2R. Um, again, just to clarify, like this is GL2 because y is going to be like 1 over the determinant, so we can't let y be 0 in this case. Okay, so, well, let's just pause, recap really quickly before we move on. So what we have shown is that if we have a functor that sends R to a group that corresponds to some solutions to a family of equations in R, then we can basically describe this functor as a coordinate ring O, and also the image GR corresponds to the set of homomorphisms from O to R. So that's what we've shown. But now we kind of want to show something like a little bit stronger. We want to show that there's like an equivalence between the functor G and the homomorphism from like O to something. So instead of just saying that like, I guess point-wise, I guess intuitively, that they're all the same, we want to say that these are actually just like literally the same functors. And so to do this, we need to show two things. We need to show that they have the same algebraic structure, like they preserve homomorphisms in a nice way, which is like one of the like properties of functors that we talked about earlier. And we also want to show that two distinct coordinate rings can't represent the same group scheme. And the second fact is like kind of surprising, right? Because generally, if you give me a group of points, then there's no like real reason for me to think that there's like only like very, very one like specific set of polynomials that is going to like have solutions in exactly in those set of points. But in the context of affine group schemes, when we consider like the whole functor itself, then this is like actually one-to-one. And then from there, we'll talk about how, oops, we can turn affine group schemes into an algebra problem. So how we can like represent or like make an equivalence between affine group schemes and some like algebraic structures. Okay, so first, in order to like, I guess, construct this, we need to like define something called natural maps. And we'll define a natural map between two functors as a map big phi, such that for any homomorphism little phi between rings R and S, this diagram that I've shown like commutes. So essentially, a natural map between two functors is basically just like a similar idea to homomorphism between these functors. Like we can either do big phi first and then map R to S, or we can do like the ring homomorphism little phi first and then do big phi, and we'll like get to the same place like all the time. So now there is like this really powerful lemma called Unida's lemma, I think. And it says that if you have functors E to F represented by coordinate rings A to B, then the natural maps from E to F correspond to the homomorphisms from B to A. And so we'll sort of do like a proof by example, just to get the general idea. We're gonna let A represent the general linear group GL sub 2, and B represent the invertible matrices G sub M. And then I've shown like A and B here, like we've talked about. And so like just to clarify, right, this is why I brought up the thing about like K algebras that I did earlier, because like B isn't really a polynomial ring because like the X like non-determinants, indeterminates? Yeah, indeterminates are like not like variables or like matrices, I guess. So I guess it's like kind of a generalization of a polynomial ring. Um, but like we can do this in the context of like affine group schemes. Um, and so now for like one direction, if you consider some homomorphism phi from B to A, then you want to show that you can get a commutative diagram showing that there is like a natural map from GL2 to GM. And so the way that we pick a homomorphism, so we're going to do one, we're going to pick it called psi in GL2R. So this like top right, no, top left thing over here. And we know that it's a homomorphism from A to R, right? Because that's exactly what GL2R is. And composing these maps gives b to a to r, right? So we do phi, which is b to a, and then psi, which is a to r, and that's going to be a homomorphism in GMR, right? Because that's exactly like the set of homomorphisms from B to R. And so we get a natural map. Sorry. And like this basically just like gives us the natural map. Because like GM and GL2 are like functors. So if there's a homomorphism from like R to S, then it induces like a well-defined homomorphism from like GL2R to like GL2S. And like same with like G sub MR and G sub MS. So like we have this phi here, right? We define it again here, like from, yes, again, like from GL2R to GMR and GL2S to G sub MS. And then like those like homomorphisms from R to S cause this diagram to commute. Um, so yeah, that's one direction. The opposite direction, going backwards, we assume that there's like a natural map. So we get this like commutative diagram, and now we want to figure out what phi is. The way we're going to do it is we're going to take the identity map in GL2A and compose that with like big phi. And the image of A in this map is going to be um, little little phi, right? Because it sends something in A to something in GMA. But GMA is a set of homomorphisms from B to A because like A is like the ring that's like in the image, right? And B is where it's like coming from. And so we get like little phi out of it. And if you think about it, um, so like sorry, hand waving a little bit. This is like kind of the reverse process of what we just did. Here we have like this, and then here we have this. Right, so big phi is like here in the same places as little phi is. Um, and so like therefore, we can show that we get a one-to-one correspondence between the natural maps and the homomorphisms. So this proves like Yoneta's lemma. And like I said earlier, this is basically just saying that anytime you have a homomorphism between two coordinate rings, B to A, um, then there's a corresponding, like, quote unquote, homomorphism between the functors that they represent. Because the natural maps are just kind of like homomorphisms for our functors. And as a corollary, you can show that the only time you get isomorphic functors, like i.e. isomorphic like group schemes, is when you have isomorphic coordinate rings. And so this, I guess, answers the first two questions we had at the beginning of the section. So we show that like the functors themselves preserve like algebraic structure, and you do have like a one-to-one mapping between your coordinate rings and your functors. And so now that we have all this, we're like, okay, if coordinate rings are like the exact same thing as our group schemes, then there's probably a way to talk about group schemes like purely as algebraic things. So maybe we want to see if we can figure that out next. And the way we do this is we introduce something called Hopf algebras. And so to give you some intuition, we are first going to observe that we can write group multiplication as a natural map. So if we have a group homomorphism between GR and GS, then we can represent multiplication in this commutative diagram, and we can do the same thing for things like identity and inverse maps. So G is just like any random functor, we can say, like a functor between sets, but we're adding, like, imposing these three natural maps on G. So we're saying G is like a random functor that, like, preserves these commutative diagrams, maybe. And so if we want to think about G in this way, then we also have to talk about, like, products of functors, because we're going to use them, just how here we had GR times GR, but eventually we like again want to get rid of the R, right? Because we did all this work showing that we can just talk about the functors. So now we need to talk about what exactly we mean by like just the product of two functors without R, without applying R first. And so we'll define the product of functors as just pairs EF, where you apply the functors coordinate-wise, and then we'll say that if A represents E and B represents F, then E times F will be represented by A times B, where we write this times instead of this circle to like just distinguish them. So if you see the circle, then we know that we're talking about like coordinate rings or eventually Hopf algebras. And then if you see like the regular times, we know that we're talking about like the product of like functors or like group schemes. And so intuitively, like all this is saying is that if we have like a homomorphism in the product, then that's just going to correspond to like E times F R, and these just correspond to like pairs of homomorphisms from A to R and B to R. Um, right, and I just sort of logic that out by like saying that like, oh, the this the homomorphisms correspond to like functors, and then the functors use the definition again, and then like make those correspond to like homomorphisms again. Sorry, hopefully that was clear. Um, and like now, in order to build like I guess some sort of theory of how these group schemes as algebraic structures work, we have to like look at, okay, like what is the binary operation going to look like, right? So if we have the product G times G, like, and we're going to draw an arrow from that to G, what's that multiplication going to look like? And so to do this, again, surprisingly, we're going to use Yonita's lemma. And so if we apply the lemma, we get that if we map, oops, G times G to G, then that's going to correspond to homomorphisms from A to A times A. Sorry, there's a little typo here. We want to map G times D to G, right? Because it's going to be the product. So i.e., like the multiplication is going to correspond from homomorphisms from A times A to A times A. And so now we're going to look at like what multiplication, identity, and inverse in G look like using Yonita's lemma to define like co-multiplication, co-unit, and co-inverse, which is what we're going to call like those operations in A. So yes, here. So first, let's like talk about associativity in terms of multiplication. So in G on the left, we're gonna have this like natural map because we can either multiply like on the left first, or we can multiply on the right first. And then like doing the other multiplication is going to give you like a map from like gamma times gamma times gamma to gamma. And here I start calling G gamma since like G is like the functor, and like gamma is going to be like some group. Right, okay. And then if we look at A, we just have to reverse everything because, for example, if we have a natural map from gamma times gamma to gamma, then we get the homomorphism from A to A times A, and the natural maps are just like the homomorphisms pretty much. And then, so we do the same thing here, where we just say, like, we're going to reverse this. A, we, like, do co-multiplication. That actually, like, sort of decomposes it into A times A. If we do it again, we can decompose it again. And this decomposition is also associative. So it doesn't matter, like, which one you decompose. You're going to get the same thing. Okay, and then we're gonna do the same thing with identity and inverse. So like here's identity. So on the group side, the unit map, identity map sends E, like in this set of like the trivial group to E and gamma, and then like going down, we multiply, which just gives you the same thing, right? Because you're just multiplying like one on the left with something in gamma. Otherwise, you're like, I don't really want to do all this. So you just say that the trivial group times gamma is just isomorphic to gamma, which equals gamma. So either way, you get this commutative diagram in terms of like, um, I guess like identity elements in groups. And then on the right-hand side, it's like kind of the same with the arrows reversed. You start with A and then you can either decompose it and then send A to the identity in K, or you can just like directly say that like A um is isomorphic to like A co-multiplied K co-multiplied with A, where K is just like we're just talking about the constants, right, where the identity lives. And so either way, you get this commutative diagram corresponding to like co-unit, which is like the equivalent of like identity in A. And then like finally for inverse, I think the idea is like clear. So just like jumping to like the right-hand side, either you do like co-multiplication and then you apply co-inverse to get like the trivial coordinate ring essentially, or you send everything in the identity, or like, yeah, you apply your co-unit to send everything to the identity, and then you just do nothing, and that's what gets you back to like this um, trivial coordinate ring A. Um, so yeah, so that's how we define like co-multiplication, co-unit, and co-inverse. And so what's the point? Well, we say that if A has co-multiplication, co-unit, and co-inverse, that respect these commutative diagrams, then we're going to call it a Hopf algebra. And there's a theorem that says that the affine group schemes over K correspond to Hopf algebras over K, which kind of makes sense, right? Because we're just looking at A first in terms of A representing a group scheme. And so if we want to talk about an affine group scheme, then we can actually just talk about a Hopf algebra instead. And then we can like use the properties or like the theory of like Hopf algebras like to our advantage in order to say things about our group scheme. So as an example, just to clarify, we can talk about the additive group, which just like did nothing, right? It sent everything to itself. And this is represented by the coordinate ring kx because basically we just like want all the homomorphisms that send x to anything in the ring. And like suppose in particular we have two homomorphisms G and H where G sends x to R and H sends x to S. And so now we want to know, what do the three maps look like? So first, co-multiplication. This is like I think the hardest one to think about, but we know for sure that if we do co-multiplication and then we apply G and H, and recall these get applied coordinate wise, so then we want x to be mapped to R to x when we do like all these things, when you do co-multiplication and then apply like GH, right? And so what's going to get us there, the thing that's going to get us there is we just want to get two copies of x by multiplying them both by the identity and then adding them. And then when we apply G and H, it'll send the first copy to R and the second copy to H, which is how we're going to get our thing. Or second copy to S. And that's how we'll get what we wanted. The co-unit and co-inverse are a little easier. Co-unit, we just want to send x to 0, and then co-inverse, we're just going to send x to negative x. Because again, these are just kind of encoding the same things in A as like identity and inverse in R look like, right? But in this case, like the identity is 0 because it's an additive group, for example. Okay, so now, like, hopefully, like this wasn't too complicated. I think like other examples probably get more complicated, but it'll like give you the general, I guess, intuition. But anyways, like I constructed these Hopf algebras, and now the next question is like, why do we even want to think about group schemes as Hopf algebras, right? Like, why did we even do all this? Is there anything useful? And so this is like one small result that I can show that uses like properties of Hopf algebras to show something meaningful about group schemes. And there are many more examples of this, but this is just one. Yeah, and like I'll illustrate something called like Cartier duality. And so what we'll do is we'll say that we have a Hopf algebra A over K. And then we want to say that its dual is a set of homomorphisms from A to K. So like the set of linear maps that are sending A to like a constant in K. And intuitively, like taking the dual will switch like co-multiplication and multiplication because Say, for example, you multiply two polynomials in A, and you want to think about taking two homomorphisms that map A to K and co-multiplying them to get back to like the two polynomials that you originally multiplied, right? Because again, co-multiplication intuitively is going to correspond to some sort of like decomposition or like splitting it up in some way. Um, or maybe like factoring, maybe in some way. So anyways, um, like I think another way of thinking about it is just that like the things in your dual are going to be like the things that operate on like the coefficients of your polynomial, I think. So anyways, we have A representing G, because that's like the whole point of the talk, right? A is representing a affine group scheme. And we will say that the scheme represented by the dual of A, we're going to call it G to the D, and it can be shown that G to the D is a set of homomorphisms from G to the multiplicative group functor G sub m. So yeah, yeah, G to the D is like those homomorphisms. And so essentially, like if I were to like specify a ring R, then the dual has all the different ways that I can define a homomorphism from like GR to GMR. At least that's how I understand it. Okay. And so now, as like another motivating example, we can take the nth roots of unity, mu sub n, and this is a group scheme, which is going to have the solutions to x to the n minus 1. And we're going to claim that it has dual z mod nz. Because again, well, this is like proof by example, right? But if we want our constants to come from like the complex numbers, maybe, then any like homomorphism in the dual is going to be determined by where it sends your generator zeta 1, which is like e to the 2 pi I over n, right? Like all the things are like e to the 2 pi I k over n. So zeta 1, like your original generator, is going to be just e to the 2 pi I over n. And then that homomorphism must also like preserve the relations. So in terms of the generator, you can write zeta k times zeta L as like zeta k plus L, which is just like multiplying them, right? Um, but that's also just like multiplying like zeta 1, like k plus L times. And then if you raise this to the power of n, you should still get 1. And so you're kind of like stuck in terms of like where you can send things. So I guess my point is that um any homomorphism can send zeta 1 to only like n different places in C in order to preserve like the relations. So intuitively, that's why we can kind of think about the dual as isomorphic to like Z mod NZ when we're thinking about like GMC, for example. Yeah. Anyways, I think like yeah, sure. Okay. And so the the theorem, the Cartier duality, says that you notice that Z mod NZ is also representing a group scheme too. And this is actually true, according to Cartier duality, of like all finite abelian group schemes, is that if you take the dual, you'll always get back another finite abelian group scheme, which is like pretty powerful, right? Because that's not maybe obvious when you think about the group schemes in terms of just like solutions to polynomial equations. Um, okay, cool. So just to recap, right? We started with a group scheme, and we said that, okay, it's just the same as a Hopf algebra, and we just like have all this theory of Hopf algebras and duals to get back really nice properties of like group schemes. So we can use those like algebraic properties to talk about group schemes. And here the idea is that you, again, if you have like a finite abelian group scheme that encodes like the solutions to a group of polynomial equations, and you like don't like it, it's too complicated, then you can translate it to the dual group scheme and figure things out about the dual instead. So like in this example, maybe it's like easier to think about like Z mod NZ, instead of like your nth roots of unity, or I'm not sure. I'm not sure which would be easier, but yeah. So that's the point. Um, so yeah, that's my presentation. Hopefully it was enjoyable. I know it's like a lot. I talked really fast. Um, but yeah, thank you. Have a good winter break.